copying of these emails. You've got shared memory. So there's all these nondescript benefits to having multiples of smaller rather than singles and short numbers of big. And this is how, this is assuming we're getting a third of the flops out of a 500 megahertz machine that we are out of a good 1500 megahertz machine. That's your UltraSpark. That's your monolithic, nice UltraSpark 2. That is going to be obsolete before you statistically can have a failure. The Sun guarantees 5 nines on the top of the product. Whereas the El Chico machines, you're going to have 1 out of 1,000 die. So whatever, you're going to have 1 die in 1,000. You're going to have 1 out of your 1,000 no die. But because you're building to take, because you expect failures, you can build to take advantage of it. What this allows you to do is you'll have 3 times as many failures in this particular than you will on that one. But at that one, if you have any failures at all, it's a single point of failure disaster. So your mission critical application will go down in the middle of the night, and the only thing you can really do to keep that from happening is have a sysadmin on a beeper. Well, this one, you don't need a sysadmin on a beeper, because if you lose 1/3 of your functionality, you just go in the morning and you swap it out, or swap out the motherboard. So it turns out that this entire enterprise is substantially cheaper than that enterprise. And like I said, you're going to have failures over here, but you might as well embrace the failures than have to worry about having a negative. That was one of the big selling points in the early days of clustering, was the single point of failure, the Andrew Carnegie solution wouldn't destroy your enterprise. It's a tougher pitch now because Sun is clustering, so it's even better if you can cluster, really, anytime you can better. Avalon was, this was something of a high watermark because this was Tom Sterling's machine. It used channel blending. He did a side-by-side comparison with a vector machine of some variety, and price beat it on every standard you compare with. Price, certainly, performance equal or better. Of course, all the, like I said, the implicit benefits of clustering. Loki, we talked about Loki. This was one of Don Gregor's. This Clap 2 and a similarly designed machine in Australia called Plugin. This came out about the same time that people were porting their floating point code over to the x86 graphics extensions, and you get a better bang for the buck if you can move your floating point code into SSE in half as many cycles as the same floating point. So this is the University of Kentucky. He wrote quite a few papers on this. The other thing he did was back when big wire speed fast Ethernet switches were expensive, he wrote an algorithm to break up your network traffic into multiple smaller switch solutions. We call it a flat network neighborhood. Bunyip called it something else. And what it did was, because the price difference between an 8-port fast Ethernet switch and a 16-port fast Ethernet switch was more than double, this thing was quite an inexpensive solution. And as it turns out, he was getting pretty close to 300 megabits out of 3 network cards. You certainly get 300 megabits out of 3 cards channel blended. A lot of people are still channel blending because the price of fast Ethernet is so cheap now. Okay, well, what can you do with, well, we already said what you can do with clusters in general. You buy 2 cheap machines at a quarter of the price of the equivalent one good machine, then you have some built-in redundancy. Even if you do have a failure, you may, at least you have uptime. It may be reduced performance, but at least you don't have single point failure. That was the big selling point for the longest time. Now, the selling point is you can still, there's the Moore's law is forcing the performance and the node size and the die size and everything into much denser packages so that you can hit the next level of clustering. You can start clustering groups of 8, groups of 64 until you hit another enterprise problem like having to buy a 64-port gigabit switch. That'll probably be the next level that you have to say, well, maybe I'll just take longer to calculate my problem. These are the traditional. The Gordon Bell Prize, I've got a couple slides following up on that. Every year at Supercomputing, they give the Gordon Bell Prize to the person who has a supercomputer that can calculate flops to the cheapest, which are the price performance unit. And Setting It Home, if you log onto their page, they claim to have hit the Zeta flop about a year ago. So by many definitions, this is they send you a chunk of data, they run a couple fast Fourier transforms on it, and they send it back. That's certainly one application. Most of the scientific computers that I've seen in practice are running equations. They may not even have temporary data, and a lot of them don't even have a hard drive. They're just those nodes. They're just calculating a portion of multivariate differences. So the Setting It Home distributed solution can have fantastic latency. Setting It Home sends a chunk of data out to 2 double-blind recipients. If you somehow figure out a way to hack in artificial intelligence into that FLT that comes back, then you can compare it to the blind one. So they can't spoof Setting It Home. They've been through their data. They've basically restarted on their data set because the screensaver was so popular that now they're looking at it in a finer vein. No. All right, so Loki was Becker's machine that he built for $63,000 in 1960. The gigaflop machine, the Beowulf cluster. And to rebuild that machine in 97, it would have cost you less than $30K. And to rebuild it in 98, it would have cost you $15K. So he entered it into the Gordon Bell competition at Supercomputing 97 and won with the figure of $50 per megaflop. Now, I don't have the 99 entry here on the next slide, but this is dropping off much faster than Moore's law would. Moore's law, so Moore's law is actually an observation. Gordon Moore said in 1965 that for any given die size, we'll be able to put twice as many transistors in it every 18 months. And they've managed to stay either on that schedule or ahead of it, due in part to some technological changes for a long time, much longer than Moore. So Supercomputing 2002 is coming up next month, and we don't know what's entered. Just they keep this competition somewhat secret until it comes out. But 15 cents a dime per megaflop. Now, when the price drops to that level, every little lab can start doing whatever particular computational fluid dynamic problem it has.
Can you comment on the hardware being used and actually the sort of size of the cluster we're talking about? Because price performance doesn't tell you absolute performance. You suggested that, well, any lab can do fluid dynamics, but not if it has the total capacity of an iPad.
That's right.
But it only costs a nickel.
Right.
So what are you actually looking at?
Well, I can tell you on some of these machines, Flat 2 is a 66 motor of Athlon. Actually, they were the slot 1, slot A Athlons.
Okay.
Less than 1 gigahertz, 600 megahertz. Three NICs each, 9 switches. Some fairly sophisticated application code to take advantage of the 3D now. But otherwise, it was something of a turnkey system. It was a simple OS install, Red Hat, I believe 6.2. And it took them a weekend to put together a simple ATX box, ECC land.
I have an application that's not ray tracing or doesn't do heat distribution on a chassis. It's not, by its very nature, intended to be a parallel process. It's a serial process. We talked about parallelizing a C program. Are there lots of what do people do if they have a problem that isn't the kind of problem that you normally think of? That you're going to put parallel supercomputers, parallel boxes. Those machines run applications which are, by their very nature, parallel. When somebody does a universe simulation, from Big Bang forward, that's done on lots of different processes. It's by its nature parallel. I have an application which isn't. What do people do who have real-world applications with? Go ahead.
Well, there's a class of middleware that is resource management. Mozix, you tell Mozix what you've got for resources, and it will determine how to distribute your problem up over the set of resources that you have. Some other packages like Infusion and like Infusion will run a copy of your app with different start and stop parameters on. So if you've got a 10-noder, they won't intercommunicate interdependent variables, but it will run, say, if your sim from 10 to 20, and the other one will run your sim from 20 to 30. It doesn't quite qualify as a parallel processor, but these packages were a response to people with very serial apps.
Yeah. Okay. Thank you.
So here's our Alexa box, and these blades have dual notebook drives. We've got some other printers in there. I think there's room for 2 sims on it. Backplane that, like I say, you can access with these big RJ 12s, I guess, where you can speak to subgroups rather than multicast. You can speak to every odd blade or even blade. And this is partially so that if you have a hard failure, you can code around it. Yeah, they're still using Crusoe. They're using the next-gen Crusoe TM50. And this is called Omni cluster. It's got a P3 in it, and you can stack a bunch of them in your PCI slots. It's got PCI and PCI bridge on it. It's got a NIC that you can access into it, and there's a lot of SPC solutions that are coming out that answer that need for people who not only have a lot of PC but a fast PCI system.
That's a complete computer.
Yeah.
How much are those?
The ones I was looking at were a grant. What level of P3 they had? It was $1,000. So,
Well, do they make them with AMD chips?
not yet. No. Part of the reason is you're not going to be able to stack these if there's anything that has a heatsink on it, or a heatsink.
Well, those are designed to be put into a PC, right?
Yeah. So you've got less than a U between PCI slots.
Well, you don't put them in regular PCs, you put them in backplane.
Passive backplanes.
Yeah. Oh. Well, maybe you'd have one big long one, so maybe space between PCI slots. And this right here, that is 8 motherboards on rails, and they've got either single or dual solos. Now this wouldn't be, so if you have any number crunching would do, it probably wouldn't be a good solution.